invariable generation of finite classical proofs.
Okay, thank you everyone very much for having me. So we'll start by defining what invariable generation is. So we say that a generating set of a group is an invariable generating set if it generates even after I throw away all the information except for just which conjugacy class each element is in. So I can conjugate each element by whatever I want, and it's still going to generate. We're going to be interested in transitive subgroups of Sn to begin with. And you can see that if we're just talking about generation, just normal generation, then a set of elements is going to generate a transitive subgroup of Sn if and only if they don't fix a common set, right, in the action of Sn on the set 1 up to n. So how about invariable generation? Well, the only difference is that we're allowed to conjugate. And conjugation is just the same as really relabeling those sets that we're fixing. And so the only thing we're keeping is the size of the sets. So a set of elements invariably generates a transitive subgroup if and only if they don't fix a set of the same size as each other. Okay. And then there's this nice result which tells us basically transitive subgroups are if we're looking at this in a probabilistic fashion and we are wanting to generate a transitive subgroup, that's the same as just asking to generate the whole thing up to a factor of a half, because the proportion of elements which are contained in proper transitive subgroups approaches a half when n is large. So as long as, so basically you can assume that with a positive probability that's bounded away from 1 or 0, whichever way around it is, all of your elements that you picked, if you generate a transitive subgroup, you can just say you probably did generate the whole of Sn. Okay, so then there's this really nice theorem of Pimentel, Perez, and Riven. They did the first part, and then the second part is Eberhard, Ford, and Green. And they basically wanted to know, if I pick some random elements in Sn, how many do I need to invariably generate? So the answer is that if you pick 4 random elements in Sn, the probability they invariably generate, and then a transitive subgroup of can be in brackets because of what we just talked about, then this probability is going to be bounded away from 0 as n goes to infinity. So there's like an absolute constant which bounds away from 0. And then if you take 3 elements, then your probability is going to go to 0. And so really if you want to be generating Sn invariably, you want to take at least 4 elements. Okay, so their motivation for doing this comes from computational Galois theory. They give you a Monte Carlo algorithm for determining whether or not Sn is the full Galois group of some polynomial, which is degree n. So we know the Galois group is going to be contained in Sn. We just want to know, is it the whole thing or not? So the first thing you can notice is that if you take a prime and you do f mod p, then you can factorize this and get the irreducible factors and look at their degrees. And the sum of those things is going to be n. So you have a partition of n, which just so happens to be a conjugacy class of Sn. And so we're going to use Frobenius density theorem, which tells you that the density of primes, which give you a certain partition for your polynomial, is equal to the density of elements with that partition as their conjugacy class in the Galois group. This basically tells you that even though you don't know the Galois group, you can pick random elements from it, but you don't get to know anything except for the conjugacy class of that random element. So that's exactly why we need invariable generation for this. And here's the algorithm. So you first would pick some primes, and then you factor modulo the primes, and that gives you cycle types. So then we can just pick any elements we want that are representatives of those conjugacy classes in Sn, and then check if they invariably generate Sn. If they do, we know for sure that our Galois group is Sn, because otherwise those elements wouldn't have been able to generate it. If they don't, then we're not sure, because maybe we just picked the wrong elements. We were just picking some random elements. Maybe we just didn't pick enough and we didn't realize that it's actually the full thing. So the probability of this possible false negative is bounded by whatever is going to be bounding the thing on the previous slide. the probability that 4 random elements invariably generate. Yeah, so if we say that epsilon is something which bounds this probability away from 0, then the probability of getting a false negative is the probability of picking 4 elements in Sn which do not invariably generate, which is 1 minus epsilon and then to the r over 4. So r is the number of primes we picked up here. So then this gives you an estimate on the error of your, like the probability of getting an error based on how many primes you've picked. Okay, but I've just been talking about the symmetric group, and in the title it says finite classical groups. So let's talk about those. I want to prove essentially the same result, but for the finite classical groups. So this is how it's going to look. We take a connected reductive classical group G, so this is like an infinite algebraic group, and then we have a Steinberg endomorphism sigma and a Weyl group W, and then we want to take T to be a sigma stable maximal torus. So I'm going to use this notation throughout. And then GNQ is basically the fixed point, so this is our finite classical group. So I will go over an example later. Essentially, you could just think of like SLNQ if you want to. And what I have shown is that for large enough Q, if you take 4 elements uniformly at random in GNQ, then the probability they invariably generate is bounded away from 0 as n goes to infinity, which is the same result, except we have this Q thing here, because there's 2 parameters now. And then for 3 random elements, the probability they're going to invariably generate goes to 0 if I take Q and n both going to infinity. Okay. So the motto here is that transitivity in the Sn side is the same as irreducibility in the SLN side. So for a lot of this, I'm going to try and show you how to prove this for SLN. The similar kind of proof works for the other classical groups, but it's just a lot more messy, and so it's nicer for me just to show this. So previously we had that thing where we said, like, you want to look at the fixed sets of some of the random elements in Sn. Well, here we're going to want to look at the fixed spaces. So this is just normal generation that's not invariable. And if you have a set of elements in SLN, they generate an irreducible subgroup if and only if they have no common fixed space. Now I'm allowed to conjugate. So the only thing that's left over after conjugating is the dimension of the space. So a set of elements invariably generates an irreducible subgroup if and only if they don't have a common fixed space dimension. And then this is the same as the result of Wuchak and Pieber, except it's for SLN. So the proportion of elements which are in a proper irreducible subgroup essentially goes to 0 as n and q both go to infinity. And so this kind of means that if we want to generate the whole of SLN, we only need to worry about an irreducible subgroup, because the probability that we generate an irreducible subgroup that's proper is very low. Okay, so all of this kind of leads us to this relationship between the Weyl group and the algebraic group. So this is a kind of a spoiler alert, but the Weyl group for SLN is Sn, and that's exactly why all of this stuff is going to work, because we have a result for Sn, and we want to just have the same result for SLN. So this is the bijection that allows us to do that. The sigma conjugacy classes in W are in bijection with so this here is our finite group, like our SLNQ. So the classes, the G sigma classes of sigma stable maximal tori of G. So we have this little thing here. Whenever we have a W in the Weyl group, we're going to have a corresponding torus, which is sigma stable and is a maximal torus of G, and that's T sub W. And then we're going to be interested in the fixed points here. So this is going to be contained in the finite group. And the fixed points, there's just a formula. You can compute what those things are. So hopefully on the next slide, yes. This is an example of me computing them. So we're going to take G to be SLN. This is over a algebraically closed field of characteristic P. And then we have sigma is the Frobenius, the standard Frobenius morphism. And then we can just take our maximal torus to be all of the diagonal matrices. I should have said that this dn is supposed to be diagonal matrices. Then we know that the conjugacy class is Sn, and sigma doesn't do anything to that, so the sigma conjugacy classes are Sn. Those are partitions of n. So let's take partition of n. So we're going to take an element W which has this partition of n associated to it. And then if you just compute what this T sub W to the sigma is, you get this thing which is arranged very nicely in blocks. And those are irreducible blocks, and each of the blocks has dimension 1 of the cycles of our permutation. So what this means is that, so we cared about fixed spaces and fixed sets, right? What this means is that the fixed spaces, their dimensions in this torus are the same as the fixed set sizes of W. Okay. But our problem is that we've got tori and not elements. We want to pick random elements. So to get around that, we're going to look at separable elements. Those are ones that have distinct eigenvalues. And they're all contained in a unique maximal torus, which is really nice. Even nicer, those elements and the unique torus that they're contained in have the same fixed spaces. And so we actually don't need to worry about the fact that it's tori there. We can just assume that they're elements. And even better, the proportion of separable elements goes to 1 as q goes to infinity. So essentially what we're going to do is when we pick our random elements, we're just going to pretend that they are separable, because most likely they are. And then finally, so I kind of hinted at this before, but you can show, so we had like the fixed dimensions and the fixed sizes are the same, but you can show that they're also distributed in the same manner. So the proportion of L tuples of elements in SLN which have a common fixed space dimension, so those are the ones we kind of want to avoid, are the same as the proportion of L tuples of elements in Sn which have a common fixed set size. Those are also the ones we want to avoid. So this result is basically just telling us that the probability is going to be the same, because if I pick one in Sn, I can go across to SLN, and the probability of having picked that just straight from SLN is the same thing. So now we can sketch our proof. So this is, we're taking q goes to infinity because then I don't have to worry about my non-separable elements. And we're just going to look at SLN, and we're going to take L random elements, A1 through AL. So L is going to be 3 or 4 in the end. Because we're assuming that q is very large, we can just say, well, they're separable. And because they're separable, they have a little torus that's related to them. And then each of those tori is some T sub Wi. So from each A, which is an element in SLN, we get a W, which is an element in Sn. We know that the fixed space dimensions of the A's are the same as the fixed set sizes of the W's. And so we can just basically write it down. So the probability that those AI invariably generate is the same as the probability they invariably generate an irreducible subgroup. Then we want to change the language into the language of fixed spaces. So that's the probability they don't fix a space of a common dimension. And then because the probabilities were equal of picking these things, that's the same as the probability that those W's in Sn don't fix a set of the same size as each other. And finally, that is the same as the probability of generating a transitive subgroup of Sn. And we know that if you take L to be 3, this goes to 0 as n goes to infinity. And if you take L to be 4, this is bounded away from 0. So it's also the same case for us. Okay. So I guess I want to say before I talk about this slide, the result of the people who did the Sn case is very analytic in flavor, and all of this just uses algebra to get the same result for the classical groups. So yeah, I basically avoided doing all of the analysis just by using this trick, but it could have been done in exactly the same way using analysis. Okay, so then for the other finite classical groups, you kind of need to, all of the little statements I had throughout need to be changed just by a little thing. Like there's going to be some signs in the way, And you need, so at some point you're going to get like halves appearing and then multiply them 4 times, stuff like that. So then you're also going to need to extend the SN result to the other Weyl groups. That's not too bad. And yeah, you want to find out exactly what it means to generate an irreducible subgroup if you have signs in the way. And then what's next for this project? It's probably going to be true that we don't have to worry about taking Q to infinity or taking Q large enough. Hopefully, it's true that it works just for a fixed Q. The idea behind that is that it seems like separable elements are diagonalizable and therefore not very likely to be good generators, perhaps. And if we can make the idea rigorous, so like the probability that a generating set without separable elements is more likely to generate, something like that. And then we also want to do the same for exceptional groups. In that case, we can't take n goes to infinity. Instead, we could take q goes to infinity, but then the Weyl group doesn't grow. So we expect that one, we're only going to need 2 elements picked uniformly at random to have a positive probability of invariably generating, and that would be bounded away from 0 by an absolute constant. And that is still kind of work in progress. So I should have said that all of this is work that I'm doing on my PhD thesis, which is I'm advised by Robert Guralnick. So this is going to be kind of like the end part of my PhD. Thank you all for listening.
Questions, comments? Yes, well, very interesting. Look, I'm certainly interested in generating elements of classical groups and practically every other group from selected random elements.
Mm-hmm.
Now, am I right in saying that you want these elements, these random elements, to satisfy various conditions? Okay. Now, I don't know. I can construct more random elements as necessary and throw out the duds.
Mm-hmm.
So, is it possible then to get to replace these assumptions of Q being large and one thing and another, and the problem, more seriously, the problem of it only being Monte Carlo,
Mm-hmm.
okay, by saying I'm going to throw out dud elements because the conditions that you want are easy to test, and I can just toss them away.
The conditions are not that easy to test, I guess. Like you just need to test whether or not that certain set invariably generates the whole thing. So you still need to test them with all of the other elements that you've picked together.
Yeah. Yeah. Okay. Well, it's getting a bit technical. I'd like to discuss it with you afterwards. Yes. So, but yes, thank you.
Any more questions? When you were talking about the application to recognizing the symmetric group as a Galois group,
Mm-hmm.
you had 1 minus epsilon to the r over 4.
Was that wrong?
Why is it r over 4 and not
Oh,
r?
okay, good. I said it's at most in order to get around that question. But yeah, yeah.
Well, I have one actually. Could you go back to the last slide, please?
Yeah.
So if the exceptional groups are invariably generated by 2 elements,
Yeah.
as large Q, we'd expect the same to be true if the classical groups are bounded dimension. Is that the case?
Yeah, so it seems like if you're going to if you fix the rank and then you take Q goes to infinity, it should be 2 elements, yeah.
Yes, okay, thank you.
Mm-hmm.